Hello everyone. So I promised I would get this video up and it is ready to go. The test is made. For those of you who did not participate in the party in my office or turn on to the WebEx this afternoon or this morning, this is going to be a review of everything on the test. I have the test in front of me as I usually do with all my videos. It is 50 questions worth 2 points each. 46 of those questions are multiple choice, 4 of them are true and false. This will also be given on the Exemplify platform. You will have 65 minutes to complete the test. There are calculations you will have to do. You will be provided with an on-screen calculator and some scrap paper if you need to. And that's pretty much the basics for this quiz. So we're going to get started in just a second, and I am still sick, so just bear with me if I'm sniffling into the microphone. Let me start off with chapter 35. And I think for those of you who joined me earlier for the tutoring session, it's a pretty straightforward test. So you should do generally well with it. There are a lot of numbers that you have to be responsible for knowing. So if you have trouble remembering, then that might be a little bit of a challenge for you, so you might want to start working on memorizing early. So we're going to jump right in, and it's very important that you know the definition for health physics, and that it's concerned with providing occupational radiation protection and minimizing radiation dose to the public. So it's health physics basically has to deal with just general radiation protection, keeping ourselves safe and the public safe, and using the minimum amount of radiation necessary to get whatever image that you need. Okay, easy peasy, right? So then we jump into the 3 cardinal principles, and by cardinal principles it means like the most important principles dealing with radiography, and we all should know those, but they are time, distance, and shielding. With time, we want to make sure that it is the fastest or shortest time possible to perform the image. Distance, we want to be as far away from the point source as possible. And shielding, obviously we want to make sure we are shielded as well as our patients, and they're shielded appropriately, and that the shields are not in the tissue of interest. It is important to point out you will need to know the exposure rate formula. Or I'm sorry, not the exposure rate formula, the total exposure formula. It is a penguin in your chapter, so make sure you know it. You're going to have to identify the formula as well as be able to apply it mathematically. So there is a mathematical equation that follows along with this. So total exposure is the exposure rate times the exposure time. So make sure that you know that and that you can do some mathematical equations. So basically, I'm going to give you the exposure rate in grays per hour, and you're just going to have to multiply it times the given time that I present. So you'll get the exposure rate and the time, and you just kind of have to figure out the rest of it. Okay? It's not really hard. It's just make sure that you remember the formula. All right, distance. So distance, we're going to refer to the inverse square law, and that's what this equation is here. Your inverse square law is I1 over I2 equals D2 squared over D1 squared, and the I is referring to the intensity, and the D is your distance. And notice that it's inverse. So the closer you get to the source of radiation, the more intense your exposure is going to be. The further away you get from the radiation, the less intense the exposure is going to be. All right? And you will have to also do the inverse square law mathematically. So please make sure that you practice some examples from your book or from your workbook, and just make sure that you can do it. You will be given the intensity or the exposure rate and the distance, and you'll just be responsible for plugging everything in to determine either another distance or another intensity rate. Okay, Shielding is common sense, you guys. Just don't shield where it shouldn't be, and shield as much as you can. That's all I have to say about that. When we talk about occupational exposure and the responsibility of an occupational worker, we really talk about ALARA. ALARA means as low as reasonably achievable. And we practice ALARA every day. That is how we base our protection, is on the ALARA principle. And the ALARA principle follows the linear non-threshold radiation dose response relationship, which falls under those stochastic or late effects. So again, that's the LNT, or linear non-threshold, and that's because even at 0, you can still have a response. So please make sure, this is really important that you remember that. Again, this is just kind of summarizing your 3 cardinal principles: time, distance, shielding. Here is your exposure rate formula. And again, that's total exposure equals exposure rate times exposure time. And this is just telling you again, short distance or short exposure time, maintain a large distance, and insert shielding whenever possible. Half value layer, or your HVL. That's a measurement of beam quality, which if you have your 2 columns, that should be in your KVP column. Your half value layer is the amount of material needed to reduce your beam to 1/2 its original value, or 50%. Again, it's the amount of material needed to reduce the beam to 1/2 its original value, or 50%. You also have something called the 10th value layer, or TVL, and that's the amount of material needed to reduce the beam to 1/10 its original value, or 90%. And that's an example would be if you had 100 KeV and you put X amount of material in and it dropped it down to 10 KeV, then that would be considered a 10th value layer. Something that will not be on this particular quiz, but will be on a final, potentially, hint, hint, cough, cough, you need to know that 1/10 value layer equals 3.3 half value layers. That is an important measurement. You will maybe be exposed to that when it comes time for your registry, so please make sure you know that. And I just want to go back to half value layer real quick and mention that you will have to be able to apply the logic behind the half value layer in a mathematical equation. So I'm going to tell you what a half value layer is for a particular department, and I'm going to ask you how you would reduce the beam, or how much would you have to add to reduce the beam down to a certain percentage. So you're going to have to be able to do this mathematically. So if you find something in your book, maybe an example in your Bouchon or in your Bouchon workbook, then I would seriously practice it. But just as an example, if we were to let's say the beam is 100. I always like to use even. Why does it do that? Whatever. You guys get the point. It's 100. Okay, and I'm telling you that the half value layer is this is just annoying. Is 0.25, and I'm going to ask you, okay, how many half value layers, or what do you need, or how thick do you need material to be placed in to bring this 100 down to a quarter? And you would have to tell me. So 1 half value layer, which is 25, would equal 50. And then if you threw in another half value layer, which would be another 0.25 millimeters of aluminum. Oh my God, this is terrible. Millimeters of, not aluminum, I'm sorry, lead. I keep saying aluminum, sorry. Lead. Why is that writing so nice when my actual straight line, no, there it is. Anyway, all right, so then I needed another half value layer to bring it down to 25. So that's second half value layer. So then you add these two together and you get, oops, guys, I'm sorry, you're going to kill me. millimeters of aluminum. So I hope you get, oh my God, not aluminum, lead. Hope you get my point. Okay, this is terrible and I'm sorry. Hold on. What I was trying to say was that let's say that I had 100 keV and I wanted it down to a quarter of that, which is 25, or 1/4 of it is 25 from 100, okay? And the original half value layer is 0.25 millimeters of lead. So 1/2 value layer would bring this down to 50, and I wanted to try and get it to 25. So in order to cut this in half, I would have to put another 0.25 millimeters of lead to get it down to 25. So then you would want to know the total thickness of the half value layers, and it would be the two half value layers added together, which would be 0.50 millimeters of lead. So that's what I'm talking about when I'm saying that you need to be able to apply it mathematically. You're going to have to apply the theory behind the half value layer concept in order to figure out the mathematical equation. That was a mouthful. Okay. Lead aprons, I've gone over this at least a bajillion times, that in our profession, our average or our aprons generally average approximately 0.5 millimeters of lead, which is also approximately 2 half value layers. And if it reduces it, if we have 2 half value layers, then how much does it reduce our occupational exposure to? And that's pretty much to 1/4. So just to let you know, we just kind of did that equation before, and that's what it is. Hint, hint, cough, cough. Okay, moving on. The effective dose. When we talk about effective dose, it's equivalent to the whole body dose, and that is a penguin in your book. It's based off of the weighted sum. And remember, that's the amount of relative biologic effect, or the amount of energy transfer, along with the radiosensitivity of the tissues. So every tissue has a different type of radiosensitivity. Some are more radiosensitive than others. So that's weighted in order to figure out the effective dose, or that whole body dose. All right, and I did say it becomes a little tricky in X-ray because we only involve partial body exposure, but you know, that is for another conversation later on. Just make sure, especially for this test, that you know what effective dose is, that it equals the whole body dose. It's based on the relative biologic effectiveness of the beam or radiation source that you're using, and the weighted tissue dose. Occupational effective dose, we normally get most of our dose from fluoro, from the C-arm, which is fluoro, or from portables, so mobile X-ray. That's usually where we're going to get our occupational exposure from. Usually in fluoro cases, we have our dosimeter, or our film badge, placed on our collar, so it's outside of the lead. Very important to also remember that our actual dose that we actually receive is only about 10% of what the monitor reports. So even though the monitor might report 50 millisieverts, or millirem, we're only getting, 10% of that, so 5. So that's kind of nice that we're not getting as much as what the badge is reading off. That's it for chapter 35. Easy peasy, right? Not much there. Chapter 40, Occupational Radiation Dose Management. And these chapters are in alignment with your Bouchon 11th edition. So those of you who do not have the 11th edition, everything from the test is in here, but just in case, you might want to get some information from your classmates if you're having issues with the chapters lining up. So again, talking about ALARA, as low as reasonably achievable. Our highest exposure is from fluoro and mobile radiography, and that's for occupational workers. That's our highest exposure. General X-ray, we really don't get much. Again, I don't know if you remember from lecture, but in IR, those IR rads tend to get a lot of exposure to their extremities, so they usually have to wear a hand monitor or an extremity monitor. And it is also super duper important that you know that the dose limit for extremities is 500 millisievert per year. And we're still talking about occupational. So occupational is 500 millisievert per year to the extremities in radiography. Some more dose limits to consider and how dose limits come to be. So our dose limits are based on that linear, non-threshold, stochastic effect relationship. The National Council on Radiation Protection and Measurement is the organization that gives recommendations to what our dose limits should be. So the NCRP, National Council on Radiation Protection and Measurement, gives our recommendations for our dose limitations based on linear non-threshold dose responses, which are those stochastic or late effects. We want to make sure that the general population only receives 1/10 of what we receive. That's in an upcoming slide, but I just want to kind of stress that. And it's considered to represent an acceptable level of occupational radiation exposure. So the NCRP is basically saying, okay, X amount of millirem is what they should be getting. It's acceptable. It's not going to kill them. Woohoo, thank you, NCRP. All right, I'm going to spend a little bit of time just leaving this particular slide up so that you can write it down. These are the doses that you need to know for your test. It's not all of them, but it's the majority of them. So annually for us, it's 50 millisievert per year or 5,000 millirem. The lens of the eye, and this is for occupational, the lens of the eye is 150 millisievert per year or 15 rem per year. You do need to know it both ways so that in case on your test you get it in millisievert or rem, you know how much is how much. Cumulative whole body is 10 millisievert. Pregnancy for the entire pregnancy, meaning from the time you find out you're pregnant or the time that the baby is conceived to the time you deliver, is only 5 millisievert or 500 millirem. And monthly for pregnancy, it's 0.5 millisievert or 50 millirem. Now, because I'm awesome and I really want everybody to do well, these guys don't, oh, goodness gracious, these guys don't need to be known for this particular test. But coming up, you're going to need to know these. But these three up here, the annual, the lens of the eye, actually the annual and the lens of the eye are very important for your upcoming. All these others you are responsible for knowing. You will get them at some point, but just the annual and the lens of the eye are the ones I really want you to focus on off this slide. Dose limits in practice, again, like I said, the public should not exceed 1/10 the appropriate dose limit given to occupational workers. Our occupational exposure is described as dose equivalent in units of millisieverts, and that should be a little v, sorry about that. And it's specified as the effective dose, or the whole body dose, remember? So effective dose. And it deals again with that relative biologic effectiveness, or the RBE, and the tissue weighting. So you need to know both. Relative biologic effectiveness and the weighted tissue factor is what's going to give you that effective dose. Okay? Make sure you remember. General population is limited to usually 1 millisievert per year. And the dose limit for non-occupationally exposed workers is 1/10 that of the established radiation worker. Again, general population, 1/10 of what the radiation worker gets. Pregnant technologist. We can, as technologists, declare a pregnancy at any time. It's only 5 millisieverts for the entire pregnancy that the baby is allowed to be exposed to. Under no circumstances should termination or an involuntary LOA, which means leave of absence, occur as a consequence of pregnancy. Under no circumstances should termination or an involuntary LOA occur as a consequence of pregnancy. That is important. So nothing can ever happen to you if you become pregnant and you declare your pregnancy. Your position cannot be terminated and you cannot be forced on a leave of absence. Okay. That's it for 40. Moving on. I don't remember even what chapter occupational radiation monitors were in because we had a little issue with the books. So I wanted to make sure to go over it again. They are on your test. There's 3 kinds of occupational monitors. There's the film badge, which what we generally use. There's the thermoluminescent dosimeters, and that's if they get exposed to heat, they will give off light. Thermo means heat, luminesce means light, and that's how we determine the exposure. And then you've got your optically stimulated luminescence dosimeters, and they are stimulated by light, optically stimulated, and those are your OSLs. Just some basics about film badges you need to know, that there's a little piece of radiosensitive film sandwiched in between 2 plastic filters. They have to be handed in every 30 days. They are very sensitive to heat, so we don't want to keep them in the cars because they will get exposed by accident. And they're not very sensitive. Well, I shouldn't say that. They have a sensitivity, but it's not a very low sensitivity. So they can only go down to 10 millirentgen. OSLs, optically stimulated luminescent badges. Those look a lot like our film badges. The really nice thing about them, though, is that they can be worn for a lot longer, and they measure doses as low as 10 microarckermas. So 10 microarckermas for the OSLs. So that means that they're nice and sensitive to low limits, which is great. We like that. Oh, I went backwards. Sorry. Okay, how to wear them. We all know that we should wear our film badges on the outside of our collars, especially during fluoro. You need to make sure you know that the collar gets 20 times more exposure than what happens underneath the apron. So again, your collar is getting 20 times more the exposure than your body underneath the apron. And again, your cath lab and IR people, they have extremity monitors because their dose limits are those 500 millisievert per year. Nuke med techs, we wear those little hand rings. Pregnant workers have the fetal monitors that go underneath the apron, and those are just another film badge. And then you've got general x-ray, the badges that can just be worn on our pockets or our lanyards that we usually wear. So it just depends on, you know, how many we're given. Okay, chapter 37, radiography, fluoroscopy, patient radiation dose. Some things to know: projection imaging is anything where the beam is being projected onto something. So pretty much all of X-ray, CT, fluoro, it's all projection imaging. The big thing that I want you to know about projection imaging is that the half value layer of projection X-rays in soft tissue is 4 centimeters. So for every 4 centimeters of soft tissue, it cuts the beam to 1/2 its original value. Again, the half value layer, soft tissue, X-ray, 4 centimeters. Okay? Patient radiation dose we talked about in class, but it can be expressed generally in 3 ways, which is your entrance skin dose or your entrance skin exposure. Your ESE, I believe, is in your current edition. Your gonadal dose, oh boy, I spelled things wrong, that should be dose, and bone marrow dose. The ESE is the most commonly reported because it's the easiest to measure because we can see it. We can see when skin gets exposed. It's easy to measure because it's external. The gonadal dose is dealing with genetic issues. So that's the GSD, the genetically significant dose. So anything that has to deal with traits given off to your offspring, that's dealing with your gonads, genetics, or germ cells, in case anybody was curious about that. And then you've got your bone marrow, which is your MMD or your mean marrow dose. And it is a target organ because it is responsible for radiation-induced leukemia. And what's going to be said in a different slide, but I just want to bring it up now, is that your marrow, the dose is determined based on whatever active marrow has been exposed. So any marrow that's actively producing cells, that is where the dose is going to be measured in that area. Measuring your ESD or ESE, entrance skin exposure. Your TLDs or your thermoluminescent dosimeters are usually accurate within 5%. The average entrance skin exposure in fluoro is 40 milligray per minute. Again, the average entrance skin exposure in fluoro is 40 milligray per minute. You need to know it. That's an important one. The other thing that you need to know is that in order to determine or measure the ESE or ESD, you're going to use what are called nomograms. And nomograms are basically graphical representations of entrance skin exposure. And in order for a nomogram to be created, it has to have at least 3 factors. And it could be any 3 factors. It just needs 3 factors in order to basically give you an X, a Y, and then some type of height variation or whatever the tissue is looking for. So it has to have 3 things. Nomogram helps you see the ESE. Again, the mean marrow dose, that's your hematologic effects, meaning your blood effects. Doesn't really occur much in diagnostic imaging because we don't give that high of a dose. And again, it is defined as the average dose to the active marrow, meaning the marrow that's actively producing cells. And you must know the average mean marrow dose, MMD, for adults in the United States is 1 milligray per year. You must know it. The genetically significant dose, or your GSD, is basically the dose given to the gonads, and it affects our gene pool in our population because it's genetic, meaning it's impacting the genes that are passed on to offspring. You really need an epidemiologic study in order to determine what it is, but they have done it in the past in the United States, and our dose is 0.2 milligray per year. Again, United States, the GSD is 0.2 milligray per year. So that's another one that you need to know. Remember, write it down, take a picture. You got to know it. Fluoroscopic patient radiation. Again, on average, fluoroscopy gives off 40 milligray per minute. It becomes a sentinel event, and that's an event that's reported to the NCRP and to government agencies. People get pulled in, questioned. Usually a lot of people get in trouble, basically. But basically, a sentinel event is something where it physically harms the patient in some way. Any dose that exceeds 15 gray is a sentinel event, and it has to be reported. That would be a whole lot of radiation, so let's hope that that never happens to us. But again, sentinel event is when a patient gets reported. In fluoro, it's any dose that exceeds 15 grays. But the average fluoro exam has an entrance skin exposure of approximately 40 milligray per minute. Another thing that is important to point out when we're talking about measuring doses is that we as workers usually use the film badge or the optically stimulated luminescent dosimeter, but when we're trying to measure patient dose, the patients, in order to find their dose, they use the thermoluminescent dosimeters. So occupational workers, film badges, patients, the TLDs, okay? You need to know that. So again, occupational workers, film badge, patients, TLDs. Chapter 39, Patient Radiation Dose Management. Important things on this slide, the glandular dose, which is delineated as DG, is approximately 15% of the entrance skin exposure. So this is another number you need to write down. So that's your glandular dose, which is 15% of the ESE. You should know at some point that it should not exceed 1 milligray per view with contact mammo or 3 milligray per view with a grid. This test in particular, you don't need to memorize that, but you will need to, of course, know the glandular dose. And then most of this chapter is common sense. So basically, we don't want to take unnecessary examinations. If somebody has a hangnail, we're not going to take an exposure of their hand or their finger. We are going to make sure that we're doing the proper exposures when necessary. And of course, it's our job to check the physicians if they're ordering things that are just absolutely ridiculous. We also want to make sure that we don't repeat exams, so we want to position correctly and take the proper position and proper diagnostic image and use the proper technique and image receptor, obviously. So we don't want to take an exposure and not have it on table or chest or whatever we're doing. So just common sense. Things to reduce patient dose. Now, I preach this all the time when we're in class. I always say high KV and low MA techniques or MAS techniques because it's better penetrability and not all that MAS is getting deposited into the tissues. We generally don't use screen film anymore, but if we did, you would have to use fast screens in order to reduce patient dose. We want to make sure to avoid the gonads so we don't affect their genetically significant dose. And we want to make sure to use lead shielding whenever appropriate. Some things to consider in pregnancy, and this even applies to occupational workers, but this is more so if we were radiating somebody who is pregnant. The first 2 weeks, so 0 to 2 weeks of pregnancy, is all or nothing. Something is either going to happen or it's not, because there is no organ development in that time frame. So either the fetus is going to spontaneously abort or it's going to be fine. So that's just kind of what happens in the 0 to 2 week period. The next major section of pregnancy is that week 2 through week 10. That's when major organogenesis occurs, meaning all the organs are being developed and all the systems are being developed. So if any type of exposure was given at that point that was high enough to cause an effect, it can cause some kind of congenital abnormality or birth defect would be a layman's way of saying it. So 0 to 2 is all or nothing, and second week to 10th week is major organogenesis. And that can be where the congenital abnormalities happen. Can things happen if there's exposure later on in pregnancy? We don't really know for 100% certainty. They do say that at the end of the second trimester and the third trimester, the baby's fully developed. The chances of any type of congenital abnormalities drops drastically. So they really don't make a lot of worry in that trimester, but usually the first trimester is the one that is of critical nature. So again, second and third trimester, there's not a whole lot that happens at doses under 25 rads, so a significant dose has to occur for some type of reaction to happen. Irradiation in utero for 200 rads is spontaneous abortion or congenital abnormality. So you need that 200 rads in order for something to occur, basically. And something interesting is that the incidence of spontaneous abortion in the United States, even without radiation exposure, is 25 to 50%, which is usually 1 in 4 people. So that means that even though the patient had an X-ray and had a miscarriage, they might want to blame it on the X-ray, but it could have happened naturally anyway. So just an interesting fact. You will have to know it at some point, so I have to bring it up, but for this particular test, it's not as crucial. And that's it. Easy peasy. Let me just go through. Sorry, I'm probably giving everybody a headache going back. but I just want to make sure I go to the beginning. And I'm just going to go through the test, make sure I covered everything that we talked about. I told you about your mathematical equations. I told you you need to know the inverse square law, your half value layers, that we base our doses recommended by the NCRP on the linear non-threshold dose-response relationship. The effective dose is equivalent to the whole body dose, and it's based off of our relative biologic effectiveness, or your RBE, and the sensitivity of the tissues being radiated. The absolute best way for us to keep our exposure down as an occupational worker is practicing ALARA and even keeping our dose down to our patients, so as low as reasonably achievable, your time, distance, and shielding. Most often, patient doses are reported in entrance skin exposure because it's easiest to determine, but it can be expressed in other ways. Something I might not have mentioned, but I'm thinking about now, is that the mean marrow dose cannot be physically derived, so it's actually an estimation of the entrance skin exposure. So again, that mean marrow dose, or the bone marrow, we don't go in and pull out the bone marrow to figure out the dose, so it's an estimation of that entrance skin exposure. So that's important to know. If we wanted to figure out the ESE, or the patient's skin exposure, we would use those nomograms, again, which are those graphical representations. Most of the skin effects that occur from radiation exposure are going to happen in higher level fluoro cases, and by that I mean like angio cases where they're doing a lot of fluoroing over a certain vessel, they're doing a lot of stenting, they're using leads. So angio is where you're going to get more of those acute skin effects. The average fluoro exam has a generally 40 milligray per minute. Trying to think what else. I told you that you need to know your mean marrow dose, you need to know your genetically significant dose, you need to know the lens of the eye for the occupational worker, how many half value layers, or the half value layer for soft tissue, that's that 4 centimeters. The glandular dose from mammo is 15% of the entrance skin exposure. Your pregnancy, 0 to 2 weeks, is all or nothing. Our occupational exposure generally comes from fluoro and mobile, more so than anything else. Our dose limits, that's our effective dose, or our whole body dose. That's how we are described, or that whole dose limits chapter is talking about effective dose. So those are all related. You need to know the dose limits to the general public, to the extremities. Looking, I'm reading, I'm thinking, everything else looks good. You cannot be kicked out of your job for being pregnant. Make sure to limit the frequency of examinations. The cath lab and IR get the most sentinel events occurring in those areas rather than general x-ray or general fluoro. So cath lab and IR have the most incidence of sentinel events because their procedures take the longest amount of time. Makes sense, right? So pretty much you're going to have to memorize some numbers, and it's a lot of just common sense, slow down, read the questions carefully, double check your math, Make sure you remember your equations, and I think you're going to be fine, okay? Help each other out, study with each other, listen to this review as many times as you need to, message me if you need to, but I literally, not kidding, you cannot hold me to missing anything. I have covered every single question that's in this test. So this should fully prepare you and get you ready, and I really hope that everybody does really well. Just stay calm, stay focused, and study what I gave you to study. Okay? Have a good day. I'm going to get out of here, and I'm sure you will all be happy. No, discard. With having this up early. All right? Thanks, guys. Good luck. I'll see you soon.